Welcome to B.Tech. Till the previous slide, we have talked on the general parallel file systems. Now we will see the Google file system principles or design principles behind the Google file system, the architecture of the Google file system. So GFS, which is developed in late 1990s, so it has used thousands of storage systems built from inexpensive commodity components where it can provide petabytes of storage, large user community to serve a large user community with diverse needs. So design considerations that have taken into picture for developing the GFS are scalability and reliability, obvious. So these are the critical features of the system. One thing is they are considered at the beginning rather than at the later stage, at some stage. A vast majority of the files, these range from a few gigabytes or it could be up to hundreds of terabytes. So basically, we have to design a system that stores or that processes huge amounts of data. The most common operation that is required here is to append the data to an existing file. To append the data to existing file. Random read-write operations are not designed for this GFS. Sequential read operations are frequently, so these are normally performed. Moreover, the users are not considered with the response time. Less concerned with the response time. The consistency model should be relaxed to simplify the system implementation, but no additional burden has to be placed on the application developers. So the model has to be consistent, but the application developers should not be overburdened. In addition to this, file segments, the files are to be segmented in large chunks. The design decisions taken here are files have to be divided into large chunks. So we need to implement an atomic file append operation. An atomic file append operation allowing multiple applications operating concurrently. So number of applications or so those will operate concurrently to append the same file. Upon the same file, there will be number of applications coming out to join or to append data to the existing file. Based on the cluster, a high bandwidth rather than low latency interconnection network. So we will consider a network with high bandwidth and separate flow of control from data flow. So as applications have to append the data to the existing file. So in spite of having the data and flow control in a similar manner, so these are separated. So pipeline data transfer over the TCP connections. So they have exploited the network topology by sending data to the closest node in the network so as to enhance the speed. The design decisions continued here. So caching is eliminated so as to avoid the overhead of maintaining the cached copies here. Then ensure consistency by channeling critical file operations. So critical file operations are performed by master, a component of the cluster which controls the entire system. Minimizes the importance of master and file access operations and to avoid hotspot contention and to ensure scalability. Support efficient checkpointing and fast recovery mechanism so as to ensure data recovery, reliability. Efficient garbage collection mechanism is also taken into consideration for design. What are these chunks? GFS chunks. Files are collected of fixed size segment called chunks, where each chunk size is 64 MB. So we have 64 MB file size chunks. The motivation here is performance for large file systems and reduce the amount of metadata maintained by the system. So when we have fixed file size chunk, the data related to this chunk could be maintained as metadata so that this can be so the overhead could be reduced. Moreover, a large chunk size increases the likelihood that multiple operations will be directed to the same chunk. So when we have a large chunk of such size, multiple operations could be diverted to the same chunk and reduces the number of requests to locate the chunk at the same time. It allows the application to maintain persistent network connection with the server and the chunk is loaded. So 64 kilobyte blocks, and each block has 32 bit checksum. So each of the chunk will have 64 KB block and each block will have 32 bit checksum. So these are stored in Linux file systems and are replicated on multiple sites to ensure reliability. A user may change the number of replicas. So these replicas can be changed from standard value of 3 to any desired value. So GFS ensures a standard replica of 3, or by the choice of user. So this replicas can be more. So a data can be stored at 3 different locations, a minimum with 3 different replicas. So if the user requires, we can have number of replicas. That is one good advantage or feature provided by the GFS. At the time of creation, each chunk is assigned a unique chunk handle. The architecture of a GFS cluster here. So we do have the communication network, the number of chunk servers. So each chunk server is allotted with the Linux file system here. So the master, which maintains the metadata of the chunks, meta information of the chunks. So the applications interact with the chunk servers. So the master maintains the state information about all system components. It controls the number of chunk servers. A chunk server runs under Linux. So it runs under Linux file system. It uses metadata provided by the master to communicate directly with the application. Data and the control paths are shown separately. Thick and thin lines. Data paths with thick lines and control paths with thin lines. So the arrows here, these show the flow of control between the application and the master chunk servers. So this is the architecture of Google file system. Then, having discussed the Google file system architecture, we'll proceed further with the Apache Hadoop. So it is an open source Java based software which supports distributed applications handling extremely large volumes of data. So it has been used by many organizations, industries, IT companies, organizations like Apple, IBM, HP, Microsoft, Amazon, media companies like New York Times, whatnot, number of companies, Facebook. So all these are supporting Hadoop. So a Hadoop file system or Hadoop system has two components. One is a map reduce engine and a database. So the database could be named as HDFS, Hadoop file system, which is named as HDFS. Amazon S3s are cloud stores and implementation of GFS. It could take any of these databases. It could be HDFS, the Amazon storage, cloud store, or any implementation of Google file system is supported by Hadoop. It is a distributed file system written in Java, hence it could be portable, but cannot be directly mounted on existing operating system. So we need HDFS. Is not fully POSIX, but it is highly performant. Hadoop cluster using HDFS here. The cluster includes the master node, and here we have 4 slave nodes here. Each node runs a MapReduce engine and the HDFS engine to store the data, and the database engine. The job tracker in the master's engine communicates with the task trackers. The job trackers communicate with the task trackers. The name node in the HDFS shares information about the data placement. So where the data actually is stored in the servers. It is being maintained by the name node where the data is located and once where it is needed. So client interacts with the master node. Master node will have the MapReduce engine and the HDFS. MapReduce engine, we have task tracker and the job tracker that interacts with the task trackers of each of the server nodes that are connected here, or in this case. The name node here, so it interacts actually where the data is stored in which servers. So this concludes the architecture of Apache Hadoop. Thank you.